You're live. Live in over an hour. Sometimes it takes a minute. They still say that's starting. Oh, let's try.
Well, actually, I don't know.
See, it says live now.
When is watching?
Oh, they're on it. Us. It's live. Cool. Thank goodness. Faith is.
What?
Luckily, Faith is. So we beat it.
Okay, before I start, any question on phase 3 of your project? Any question on that? So some of the teams are trying to set up Tomcat environment locally, so you can do development locally, which is totally fine. And we're happy to help you, but keep in mind, if you do decide to do that, your local setup could be, depending on how you set up your environment, how you install Tomcat and all that, and what kind of IDE you are using, the way to config that properly with respect to your IDE may vary dramatically, right? So it's kind of hard for us to give one unified instruction as how to do it. So it's always kind of like a case-by-case situation, right? Depending on your OS, depending on how you install it, how the configuration is set up. So really, if you run into any issue, if you try to set up locally, I strongly encourage you to just talk to the TAs or come to my office hours. Then I can take a look. Yeah,
I just wanted to recommend to people trying to do this, like, don't use IntelliJ and don't use like the regular version of Eclipse. Just install like the Eclipse with the enterprise stuff, because it comes with pretty much everything you need built in and ready to go, and you just have to change a few things. But it's very difficult if you just start with the regular version of Eclipse to get
Actually,
going.
if you don't mind, can you post a Canvas announcement to highlight this point? Yeah. All right. So, sorry, I have it. So we will continue our discussion on function dependency and normalization. The good news is I think I'm able to wrap up this discussion today. And we will be able to move on to the next topic, which is transaction process. Okay? So, this. So a quick recap what we discussed last lecture. We talked about the definition of normal form, and in particular we talk about BCNF, and the definition of BCNF is highlighted on this particular slide. Every functional dependency on a set of functional dependencies F with respect to an input schema R must satisfy either of the following two conditions. One is it is a trivial function dependency in the sense that the right-hand side is a subset of your left-hand side. When you have X determine A, X is a subset of X, A is a subset of X. In that case, that's what we call a trivial function dependency. Or X is a superkey. In other words, BCNF, put it simply, only allows key constraints as your function dependencies. Right? BCNF only allows key constraints to be your function dependencies. That's kind of, the intuition behind the definition of BCNF. This is a very intuitive definition. If you think about it, if you only have key constraints on your relational schema, obviously, the level of redundancy is minimized. The level of redundancy is minimized because no other attributes can determine any other attribute. In other words, there is no dependency whatsoever between different attributes. There's no dependency whatsoever between different attributes, right? So that's the key message you need to remember for BCNF, right? Of course, there are two ways you can understand BCNF. One is to memorize this definition and check it mechanically, one by one, against each function dependency. The other way is to understand that high-level intuition I have just said, which is it only allows key constraints, in the sense that by allowing only key constraints to exist over your schema, you have minimized the level of redundancies that can potentially happen in your instances. I think the latter message is more important, if you ask me. If you are going to have a full understanding of BCNF and why people define BCNF in this particular fashion. Right? People don't just come up with some random rules and enforce that, right? They put forward these rules for some strong reasons, right? For some strong reasons. So that being said, we also talk about decomposing relations. The point is, when you have a schema that does not satisfy BCNF, in this case, R determine W has violated BCNF requirement because R is not a key, then you decompose that into two smaller schemas. In this particular case, this decomposition is fine because when you join them back, you get the original relational instance back. But there are cases where if you do decomposition, you end up with a lossy decomposition. Lossy, in this case, refers to the fact that when you join the decomposed instances back, you do not get the original instance. It does not necessarily mean you're losing records per se, right? You may get what we call this code are called ghost records. For example, these two are ghost records that do not exist in the original instance, but as a result of your decomposition, when you draw them back, you get those records that do not actually exist in the original instance. So a fundamental objective of decomposition is to make sure we get only lossless join decomposition, right? Rather than getting things like this, which is what we call lossy decomposition, right? So given that observation, we talk about this particular theorem. What we said, I'll give you a recap of this, is given a schema R, if you decompose R into two smaller schemas, X and Y, this decomposition is a lossless join decomposition if and only if, so this is both a sufficient and necessary condition, if X intersect Y, meaning the two decomposed schema, if you intersect them. By the way, this intersection is applied with respect to the set of attributes those two schemas have. It is not to do an intersection over the instances from those two schema, right? These are two different things, right? Where this intersection is to view a schema as a set of attributes. You're performing the intersection over two sets of attributes rather than two instances. Okay? So that's one thing to keep in mind. If the common attributes, in other words, if the common attributes from the two resulting schemas as a result of your decomposition determines either one of the two schemas, either X or Y, you don't have to determine both, you only need to determine one of them, then we claim the decomposition is lossless. This is the sufficient condition. The necessary condition says, if you have a decomposition R into X and Y, and if you claim this is lossless, then it must be the case the intersection of them must determine one of the two. That's the necessary condition direction. Okay? And this is the if and only if, so both directions hold. Both necessary and sufficient condition hold. However, towards the end of last lecture, we mentioned that this particular theorem is useful for checking if a decomposition is lossless or not. But it is not an operational step that you can take in decomposing a given schema, right? It doesn't tell you how to obtain such X and Y. That's what I mean, right? So to go further, based on this particular theorem, we derive this what we call lemma, or useful result. It says the following, basically. So you have R have F, and if from F closure, and you can decompose R into R1 and R2, where R1 equals to R minus Z, and R2 is WZ. And this decomposition is guaranteed to be lossless. And I proved this for you, so I will repeat that proof as a recap of what we said last lecture. How do we prove this? Well, you basically view this as your X, you view this as your Y, right? So all you need to show is to show that X equals Y determines either X or Y, right? So that's what you need to show. And you substitute this X and Y with R minus Z and WZ respectively. And basically what you need to show is this determines either this or WZ. Right? If you can show that by the theorem above, this decomposition must be lossless. Right? Any questions so far on this? Good? Everyone is keen on this? Okay. So the critical step in your proof is to show that the first critical step in this proof is to figure out what is really the intersection of these two. To understand that, we come back to R. R is a set of attributes. The fact that W determines Z are from F or F closure means that they must be attributes of R. They must be attributes of R. So somewhere in R you must have W. Somewhere in R you must have Z. By the way, W and Z are two symbols representing either a single or a set of attributes. It doesn't mean the attribute W or attribute Z. They are just two symbols representing one or potentially multiple attributes from R. Does that make sense? So far so good? Okay, for example, W can be AB, and Z could be CD. That's totally fine. You follow me on this? Okay. Now R may or may not. R may or may not have other attributes. In the general case, R may have some additional attributes, like that. If I use more additional symbols to represent that, I can represent this part as A1, A2, and A3. Again, these are symbols representing either one or multiple attributes. In other words, R, in this particular case, I can represent R as A1, W, A2, Z, and A3. Something like that. You follow me? All of you follow this? Yeah? In the general case, actually, it doesn't have to be so complicated. I basically can represent all of this using a single symbol called A. So maybe I should now use A because A is used over there. So I use H to represent all the other attributes. Then my view of R is simply H, W, and Z. Right? H is all the other attributes, not from W and Z. You follow me? By that argument, R minus Z becomes what? H and W, and this is simply WZ. And the intersection of them, obviously, is what? Is W. And this step, by the way, this step requires the fact that given, you need this fact that W intersects Z is empty. Otherwise, if W intersects Z is not empty, this intersects this with this W, but this may still intersect with Z and give you some additional thing here. So it could be W plus something additional thing. But because W intersects Z is empty, it's an empty set, the intersection of that must be just W. Okay? Now, what that says is all we need to show is if W determines this or this. We don't know about this, but this is definitely yes, because W determines W. And given W determines Z, using the union rule of Armstrong theorem, we can show that W determines UD and a proof. This must be a lossless strong decomposition. So far so good? Everybody follow this proof? So I have given this proof twice now, right? We did this last lecture, I did it again. So I hope you follow this, okay? Now using this, we can show why this decomposition is actually a lossless strong decomposition, because if you do the intersection of them, the intersection is C, and C determines BC. So the intersection of them determines one of the two resulting schemas. Henceforth, this must be a lossless strong decomposition. And that's when you use the theorem to check, right? But what about using this result? WZ and this operational approach, right? Well, if you think about it, I can view, in this case, my R is A, B, C, my F is right? So given that I can view this as W, I can view this as Z, and obviously the fact that W intercepts D, which is C intercepts B, obviously is empty set in this case. So those two conditions hold. So I can apply this operational approach to decompose this, which is R and Z and WD, and you substitute this value in. WD is just BC. Or CB. CB and BC are the same, right? Because relational schema, the order of attributes doesn't matter. BC is the same as CB. And what's R minus Z? It's just ABC minus B, so this is C. That's essentially the decomposition we have obtained. So far so good? However, you can also apply this with regard to A determine B. Then you get another decomposition which is also lossless. Let's try that. So this is the decomposition 1, right? Decomposition 2, I can view this as W, this as Z. Then my WZ is what? My WZ becomes AB. My R minus Z is what? No, tell me? Huh?
AC.
A,
C.
C, right? The same, right? Because B, Z, it's the same. Yeah. And I claim this is a lossless strong decomposition. Why is that? If you do the intersection of them, that means that's equal to A, but A determines AB. So I know proof. Okay, if you don't believe me, you try this decomposition into AB and AC, and you do this exercise, you will find out that the join will guarantee to be the same as original instance. You can do this exercise on your own, but that's essentially what we have said so far. Okay? Now, moving on to new things, right? So far, it's been a review of what we have said. Now, moving on to the next topic, which is, okay, so lossless strong decomposition is really important, but there's another thing that's kind of missing here, which is, if you look at this particular decomposition that we have derived, if you go with this decomposition, there's one challenge, which is enforcing the dependency A determine B becomes really hard. Enforcing the dependency A determine B becomes really hard. Why is that? Because the attributes A and B are now in two separate tables. Right? Do you follow me? And because of that, in order to enforce this constraint A determine B, what you have to do? You have to write either an assertion or trigger, right? Or join, like you said. Or you write a join, essentially the same thing, right? In the expression of your trigger and assertion, it involves a join of the two tables. That's essentially what you said. Which is expensive, right? And error prone when you do that. Okay? So this observation motivates people to study the following, which is, we define this thing called dependency preserving decomposition. So how to define that formally? The intuition is actually very simple. The intuition is the following. Okay, I want to have lossless round decomposition. Obviously, I need to have that. There's no room for error over there. On top of that, can you also guarantee the following, which is you decompositions, the decomposition that you have produced will have all the original set of dependencies that I can check without involving an expensive join or using assertion or trigger. Does that make sense? Obviously, that's not the case here, right? Because in order to enforce A determine B, you need to use a join in assertion or trigger. But we need to formalize this definition. Go ahead. Yes.
What was it called again?
Dependency preserving decomposition. Okay, which we will talk about in the next slide. So we need to formalize this concept, okay, which is what we'll do next. Okay, and this definition essentially capture what I have just said. Right? So if you decompose R into X, Y, and Z, right? It can be multiple, by the way. As I said last time, the decomposition procedure can be done recursively, so that you may end up with something like this. Right? You may end up something with a schema like this, right? The point is you keep decomposing a resulting schema until a certain level of a normal form is met. For example, at this level, at the end of the day, you have this guy. You decompose this into these 5 smaller schemas, and any one of them is in B, C, and F. Suppose that's your objective, meaning all my schemas in my database must be in B, C, and F. So what you do is you keep decomposing a schema until the resulting schemas are all in B, C, and F. That's when you stop. That make sense? So this definition uses a case of decomposing the original schema into 3 relations, but it doesn't have to be 3. It can be 2, 3, 4, 5, whatever. Right? Does that make sense? Okay. Now, if R is decomposed into X, Y, and Z, so this is a 3 decomposition example. And if we enforce the function dependency that hold individually on X, on Y, and on Z, then all function dependencies that were given to hold on R must also hold. Let's check if that's the case here. So R is decomposing to 2 schemas, X and Y. X is AC, Y is BC. This is, so that's my input. I decompose R into X and Y, where X is, right? Now, what I use Fx to denote the set of functional dependency hold with respect to schema X. What is Fx? And what is Fy? Can someone tell me what's Fx? What's Fx? What's Fx? The set of functional dependency hold with respect to schema X. Yeah, good observation. There's no, right? There's nothing here, right? It's an empty set. Essentially, this is an empty set. Because there's no A determine C, nor C determine A. There are no such functional dependencies.
So it doesn't include trivial dependencies then?
Well, yes, good observation. Let's ignore trivial dependency in our case. Okay, okay. Things like this. Okay? We ignore those trivial functional dependencies. Okay? What about Fy? Is there anything here? Go ahead. Yes.
C determines
C determine B, right? Yes. That's good. There's no B determine C though. There's only C determine B. Okay? Now coming back to this definition, now you have a good understanding of this definition, right? What this definition says is, it is dependency preserving if I enforce fx on x and fy on y, if I enforce both, it gives me f over r. Is that the case though, in this case? Obviously no. If I enforce fx on x and fy on y, do I get f with regard to r? No, I do not get that back because I lost A determine B in this process. So this is not dependency preserving decomposition. You follow me? Henceforth, you need to use a trigger or assertion withdrawn to enforce A determine B. However, if you do have a dependency preserving decomposition, can I have an example of that? Yes. Let's go back to this example. Is this decomposition dependency preserving? Can someone tell me?
Yes.
Yes. Can you explain why?
Because the dependency.
So the dependencies are these two, right? That's my
Yeah.
app.
So the dependency of S determining all the other stuff, so S being a super key is preserved, because it's still in that table. Because all the things remain together in that table, and then R and W are now in the different table. So that dependency is also.
Yes. But it's a little bit trickier than what you have said, actually. So let's go over this together. First of all, let me argue that this. First of all, can someone argue for me this is a lossless strong decomposition? Can someone do that? Decomposing this into this two schema is lossless strong decomposition. Can someone do this for me?
Yes, because if you do join, they'll join on R, and
Yes.
you'll just get the original instance back.
Okay, that's a good attempt, but that only shows with regard to this particular instance, that's lossless. How can you guarantee if I modify the instance? Let me insert another meaning tuple here. You're not sure, right? Because unless you are willing to do the join all the time, then. But if you do that, I can change the instance again. You got to. How can you show that?
So you do R intersect W, and that's empty, because they're the two things that are dependent. And you pull, so you, from your original table, which has all the dependencies, and then R and W, you remove W and you make a new table with R and W.
So that's the operational step you are talking about. W is
Yeah.
missing, right?
Yeah,
But
so
here, I gave you the decomposition. I just want you to check if it is lossless.
Oh, so we don't have access to the original table?
You do have the original. Okay? You have this table, the original schema, and this two schema. I give you these three schemas.
Yeah, it's the lemma of that thing you showed us, right?
Yes, should you use, the question and then is, should you use this lemma here, or just the theorem above? Remember, like I said, if you go is to just check if a decomposition, if a given decomposition is lossless or not, you use the theorem directly, because that's the sufficient and necessary condition. You use the lemma because it's operational. If you want to do decomposition yourself, you use the lemma. In this case, decomposition is given to you. So how do you check this? Someone tell me?
Sorry, can I ask what you just said? You said you use the theorem if you want to check the
Yes.
decomposition, and you use the lemma if you want
To
perform.
decompose.
Okay.
The lemma is for operational purposes. Right? That being said, can someone help me with this? Yeah, go ahead.
We basically ignore the actual instances. You just look at the output schema.
You just look at the schema, okay, and
You compare the new schema that you got from doing the intersection to the one that you originally had, like the goal did.
so let me write this down. So this is the original schema. R, the decomposition is X is Sn L RH, and Y is what? RW, right? Now go ahead. How do you check? This is a lossless rounding.
You do the intersection and you
X intercept Y is what? Can you tell me? What is this? Huh? R, okay. And how do you show this is lossless rounding decomposition? Yeah?
Well, R determines R.
R determine R and W. Why is that? Because you are given your function dependency is what? S determine everything. That's the key. And R determine W. And given this and the trivial dependency R determine R, this and this shows you R determine RW, which is to say X intercept Y determine what? Determine Y. Hence, this must be a lossless draw decomposition. Okay? Yes or no? You guys need to do this, okay? I show my card to you. It's like we're playing a test poker game. I will show you my card, meaning this will show up in the final exam. Right? So you know my card. You should prepare for it. Yeah, go ahead.
If you were to try to use the lemma,
If you were to try to use lemma to do the operational, let me show you how to do that.
yeah,
Yes.
but I mean, like, even to verify that the decomposition is lossless.
Well, the thing is, if you follow the lemma, that's the cool thing about the lemma. If you follow the lemma, we prove the lemma is correct, right? That's the thing. That's why I give you that proof at the beginning, so that you don't have to prove every time.
Yeah.
So if you follow the lemma, you're done. You don't need to check. It's guaranteed to be lossless.
Yeah, but I mean, like, say that we're given like the two schemas like now, and you ask us to verify that it's lossless.
No,
If we were-
if you have a schema like this, you don't have to verify lossless. Because lossless is the definition with regard to the decomposition. If you haven't done any decomposition, there's no lossless to check.
I mean, yeah, I mean, like, if you're giving us a decomposition and we're checking that it's lossless,
You use the theorem to check.
you have to use the theorem.
Yeah, of course.
Wouldn't the lemma still work though?
Well,
They're
if
equivalent.
I see what you're saying, if you think you can show, oh, this decomposition is a result of following that particular lemma, yes, of course. But these two are equivalent, right? If you think about it. The fact that the reason that lemma works is because we proved the lemma using the theorem,
Falls from the theorem.
right, in the first place. So it's the same thing.
I'm just wondering if in some cases it might be easier, like if you look at it, you're like, oh, that like looks just like it would from the lemma.
Well, yes, but I would say in most cases, I think it's more intuitive to just check the intersection and see whether one of them is determined by it.
Okay.
But speaking of that, the reason why this decomposition is a result of applying the lemma is what? Is by viewing this as W, this as Z. So one schema of your decomposition is WZ, which is RW. The other is what? R minus Z, which is the whole thing, minus W, so it's SNLRH, which is essentially this. Okay? Now, to the real important question, right? Which is the question I was asking at the beginning. Why this is a dependency preserving decomposition? Okay, let's do that together. Okay, so this is my original set of F, right? What is my F, R, Fx, and Fy? Can someone tell me? Let's start with a simple one. What's Fy? What are the dependencies in Fy? The host with respect to the schema Y in this case. R determines W. The only one, right? No guessing, this is trivial, right? R determines W. What are the dependencies in Fx? The host with respect to X. Huh? Somebody said none. No. Meaning no dependency here, which is wrong. You do have dependency here, which is?
S determines SNLR.
S determines SNLRH. S is a key that determines everything, so S still determines everything. Does that make sense? Go ahead.
Is it because R is an
Say it louder.
Is it because R is in that list and R determines W?
Well, no, I'm defining fx, right? So s determines everything else, but I don't know what you're trying to argue for. S, has nothing to do with R determines W.
Okay.
I mean, this is just based on this. S determines everything, give you this. Has nothing to do with R determines W. But R determines W will play an important role in the next thing I'm going to claim. Now, I ask you guys the next question, which is a little bit tricky, which is enforcing fx over x and enforcing fy over y. Does this give you f? Does this give you f? Yes or no?
Yes.
Does this give you f?
Yeah.
You have to be a little bit careful in what you claim, right? What is missing, if you think about it? Let me be extremely clear on this. The unknown dependency is this, right? Using Armstrong axiom, when we have this is equivalent to what? Using the decomposition rule of Armstrong theorem, right? Using the decomposition rule of Armstrong theorem, S determining all of this is the same as S determining each one of them. You follow me? And what this equal to? Right? Yes or no? Again, using decomposition rule. These two, when you union them together, when you do fx union fy, is this the same as f? Yes or no? Yes or no?
Yeah.
Be careful.
Yes.
How many say yes? How many say no? You are my friend. Okay, go ahead. Why is no? What's missing? You are my friend, but I hope you know why you are my friend.
So what's missing is S determines W.
Cool,
But
fantastic.
if we're using like that one of Armstrong's.
Hold on. Yes, that's the next one I'm trying to get to. Okay. So this is missing, guys. S determines W is missing. Okay? So by the definition of dependency preserving decomposition, this seems like not a dependency preserving decomposition. Right? Because you have no way of enforcing S determine W now. However, let me finish and I'll take your question. But if you think deeper, if you think about this further, right? If you enforce all of this and you enforce this, meaning you define a new set of function f prime that equal to the union of these two. Okay? So far so good? Which is all of this plus this. That's in f prime. There is a key observation, which is the closure of f prime is actually the same as the closure of f. Why is that? Because from S determine R and R determine W, you can derive S determine W. So enforcing S determine R on the first schema and enforcing R determine W on the second schema automatically gave you S determine W. That's a catch. And because of that, this is still dependency preserving. In other words, you do not have to worry about enforcing S determine W. It's automatically, magically enforced as long as you enforce those two set of dependencies independently. You follow me? Yes or no? Using this example, this is an excellent example. Using this example, now we can arrive at the conclusion I've been longing for. The conclusion I'm trying to argue for you is, in order to check dependency preserving, in order to check if something is dependency preserving, you cannot simply check this. You cannot just check this condition. You cannot check this condition. Rather, what you need to check is the following, which is the closure of them. Is this the same as the closure of the original set of dependencies? If these two are the same, then this must be dependency preserving. Otherwise, it is not. You cannot simply look at the union and say this, if they are not the same, then this is not dependency preserving. Do all of you follow me on this example? Now I will open floor for questions. I saw a couple. Gary, go first.
So a lot of us jumped to that conclusion already when we saw that S determines R and R determines W, so it is actually functionally equivalent.
Yeah.
But you took a long time explicitly walking through this point yet. What do you want us to be cautious of?
Oh, yeah. So what you need to be cautious, if you think about this S determine W, it's not, this dependency is not part of this union in this set, right?
I mean,
It is not.
Isn't it implied?
Well, it's in mathematics, we have to go with the strict definition of union. What's the union of these two? It's just this, guys. It's set union semantic here. And nothing more. So math, that's why I think math is beautiful. Right? The reason math is beautiful is there's no ambiguity. When you say something, it means something. That's why there's no lawyer in the world of math. I really hope, our Congress, when they form laws, they can form the laws using mathematical language. Seriously, then we don't need Supreme Court judge, we don't need any of these guys. And they don't need to remove this filibuster so-called nuclear option. All of this is gone. Because there's no ambiguity. Union means union, period. Why you need lawyer for? No? So too bad. I think the bigger point I was trying to make is too bad the founding fathers of this nation are not mathematicians. No kidding. They must be lawyers. So they set up this complex system law system so that lawyer can make a lot of money out of it. That's the very cynical view of the world, but that's just me. I don't ask you to hold the same view, but to Carrie's point, that's precisely what's going on. When you say, okay, isn't that implied, you are thinking now like a lawyer, right? Does this law actually imply that? Well, that's up to debate, right? But in our world, we don't want to get lawyer involved. Right? So fine, let's talk about isn't that implied? That's essentially this claim right here. Again, now there's no ambiguity. What do you mean by isn't that implied? What do you mean by that? Well, that means precisely this. The closure of the two must be the same.
So there you said that f sub x was also like all these things. S implies S implies N, S implies L, and so on.
You mean why these two are equivalent?
Yeah. Wouldn't that be a closure of f sub x and not f sub x itself, because you use Armstrong's rules to get there?
You mean the closure of this?
No, I mean like so the f sub x.
S determine S.
So
No, I use Armstrong's theorem to get this, which is the
So doesn't
decomposition.
that,
Right?
doesn't that make it a closure though? Because you're using.
That's the closure for just fx, not the
Okay.
union of it.
Yeah, okay, but it's not f sub x.
No, hold on.
That's
So
the distinction.
what you bring up a really important point, which is okay. Pay attention to this. The closure of this union the closure of this is not the closure of the union. Give you a simple example. Okay. The closure of fx in this case is just itself. Let's ignore trivial function dimensions such as a determine A and B determine B. The closure of fy is just still the same. So does it make sense? Oh, actually, in this case, it is the so it's not the same. So the union of them is what? This is what? It's just A determine B and B determine C. That's it. But what's the union of the closure? The closure of the union. You union them together, which is this. But once you now apply the closure, this becomes what? These are not the same.
Yeah.
From a set semantics.
Yeah, but what I'm saying is over here you said that f sub x was s implies s implies n, s implies l, and so on.
Yeah.
But wouldn't that be a closure of s sub x?
Yeah, it is. But
So it's not f sub x.
well, no, this is not a closure of this. This is basically rewriting fx in another form.
So
This
when
is just rewriting fx in another form. In fact, I will say this though. This is not true, but the closure of this
yeah.
is the same as this. Okay.
Yeah.
So it doesn't matter. I mean, no matter how you use it, whether you're using fx closure here or not, doesn't really matter.
The
It doesn't
distinction I'm
change
trying
anything.
to make is when can you simplify using Armstrong's.
You can always simplify as long as you show the
Without
two are
it being
equivalent.
true.
Yeah,
Okay.
yeah. Okay. The point is, if this is equivalent to this, we get to Armstrong theorem, right? Either the closure or something else. If this is equivalent to this, the union of them, at the end of the day, as long as you do the closure, they are back to the same. Okay? So think about this and this, okay? So this is dependency preserving, okay? This is dependency preserving. In other words, the way you check dependency preserving is to look at each individual set of function dependencies, union them, check the closure of that, whether the closure equal to the closure of the original set of function dependencies. If they are, it is dependency preserving, otherwise it is not. You cannot simply check just the union of those function dependencies. Okay, fantastic. Finally, we're done with this. So here is another example, right? If I have ABC, which is I have the three functional dependencies, A determine B, B determine C, and C determine A, I decompose that into A, B, and B, C. First of all, is this decomposition also a strong decomposition? How do you check that? Well, you check the intersection. That's your X, that's your Y. The intersection B, does B determine either X or Y? In this case, actually, B determines both. Because B determines C, so B determines BC, trivial. But if you look at the original set of functions, B determines C, C determines A, so B determines A as well. So B determines A and B determines B, so B also determines BA. So in this particular example, X intersect Y determine both X and Y. So it must be lossless, because you only need to determine one of them. You don't need to determine both of them. Right? In this case, the intersection actually determines both of them. So it's more than necessary, but fine, we will take that. So it is a lossless strong decomposition, right? It is dependency preserving. It is dependency preserving. Well, let's do this check together, okay?
Oh, that's it.
So I decompose this. Right? What's my fx? What's my fy? My fx, what's my fy?
Step by design.
Is that all?
Yeah.
Yes, that's the point I was trying to get to next. Okay. So in this this example shows yet another tricky point for this dependency preserving check. Right? If you were to just use this, looks like right? That's A determinant B goes here, B determinant C goes here. I do not have B determinant C in the optimal set of F. That's it. And if you check this Fx union Fy, okay, fine. I'm going to use the closure of this. Is this equal to the closure of F? Obviously not, because this only gives you A determinant B, B determinant C. The union of this is what? Is A determinant B, B determinant C. And the closure of that is simply A determinant B, B determinant C, and A determinant C. That's it. There's no more you can infer, right? There's no more you can infer. That's clearly not equal to the closure of F. For example, C determinant A is already missing. Not even with, you don't even have to check F closure, just check F. This is already not the same. Do all of you follow me on this example? So, is this not dependency preserving?
I think I probably agree because you want to add B determined A to FX. Because you can infer that by getting F closure.
Yeah, fantastic observation. So here bring up another important point, which is when you define Fx and Fy in the first place, which is the set of dependencies that hold with respect to X or Y, here is the important message, okay? It's kind of like watching a movie. You can ignore all the other part. You want to watch the end, right? Here is the important part, important message. When you define Fx and Fy, you cannot just use F. You need to use F closure. You need to use F closure in order to define Fx and Fy in the first place. In other words, in this case, it's not only A determinant B, but also B determinant A. Why? Because if you look at the closure of F, yes, A determinant B, but in the closure of F, A determinant B, B determinant C, C determinant A. So with these two, you can actually derive B determinant A. So that should be projected, quote unquote, to X. So X is actually this. Fx is actually this. What about Fy? Is it just B determinant C? Or you have additionals? Well, C determinant A determinant B, these two give you C determinant B. Okay? Do you follow me? Now let's do this check. Now if the union now equal to the closure, well, you have to have is the closure of this equal to F closure? Well, if you look at it, A determine B, here there is one over there. B determine A, which is inferred, so it's okay. B determine C. Looks like C determine A is missing, right? C determine A is missing. But however, if you use these guys, this actually inferred C determine A. By that point, you realize the closure of this is actually the same as the closure of F. So this is dependency preserving. These topics are tricky. I agree with you on that, but these are important. In practice, because if you go out and try to decompose relations, you need to ensure they are lossily strong. Typically, you need to ensure they are dependency preserving as well. And if you somehow cannot get a dependency preserving decomposition, you need to figure out what dependencies are lost in the process of decomposing your schema so that you can add a trigger or assertion to enforce that involving join. I mean, you definitely do not want to end up with a decomposition where some constraints specified with respect to your original data are lost. So this is dependency. So, yeah.
So how come the original thing that we're trying to satisfy, where we have fx union fy closure equals f closure, since you said that we do in fact need to find fx closure and fy closure?
Not fx closure and fy closure. When you define fx and fy, when you define them in the first place, you need to use the closure of f to define them, rather than just use f itself to define them. That's what I said. If you were to use f, you won't find B determine A and C determine D, because those are not part of f. Then you will end up with the wrong conclusion that the union of them, the closure does not equal to f closure. You have to use the closure of f to define what's fx and fy. That make sense? That gives you this and this. That's what I said. It's not the closure of fx or fy, it's the closure of f that we need to use when define fx and fy. Okay? That's what I said. Okay, we're almost done. Okay, I promise you this is the last two slides and we're done. Okay, so now we are finally ready to talk about the decomposition algorithm for BCNF. All this discussion, at the end of the day, our objective is to do the following, which is if an input schema does not satisfy BCNF, it's not in Boas court normal form, then we want to decompose that schema into a set of schemas that are in BCNF. Right? The question is, how do we do that? How do we do the decomposition such that the input schema that's not in BCNF will be translated or decomposed into a set of smaller schemas that each is in BCNF. And we want to make sure the decomposition is lossless joint decomposition and dependency preserving. Is there such an algorithm? Okay, so here is algorithm. Here is the decomposition algorithm for BCNF. The first step is very trivial. Given the input function dependencies, you first make sure the right-hand side of any function contains just a single attribute. In other words, if you are given AB determines CD, you split that into, using the decomposition rule of Armstrong theorem, you decompose that into AB determines C and AB determines D. This is the trick, right? You do this for all function dependencies that's given to you. That's trivial, right? Step number 1. Now step number 2. Now go through every functional dependency in F. Go through them one by one. If you find a functional dependency x determine y in F has violated BC and F requirements, what does that mean? That means it is not a trivial functional dependency, meaning y is a subset of x, and x is not a superkey. None of this is the case, then x determine y must have violated BC and F requirements. Right? As soon as you find one such dependency, you decompose R into R minus y and xy. Can someone tell me why this works? What we're essentially doing here?
You're using the lemma.
You are just using the lemma. Yes, exactly. W determines Z, you decompose that into R minus Z and WZ. I'm just using the lemma here. No trick. So that, because you're using the lemma, what do you get? The decomposition, this decomposition is guaranteed to be lossless strong. And what's cool about this decomposition is, if you think about this, I do not know whether R minus Y is BCNF or not, but I do know XY must be in BCNF now. Because the only dependency that holds over XY is what? X determine Y, but X now is the key of that schema, so X determine Y satisfy BCNF with regard to XY. I do not know whether R minus Y is in BCNF or not. Fine, I can recurse. I view R minus Y as my new R, grab all the remaining function dependencies into that, and recurse. Do you follow me? I just keep doing this. Yes?
So quick question. So
Yeah.
when we're decomposing, since that's applying it, we're using the lemma in that situation
Yes.
up there? Okay.
Yeah. So when you're decomposing, that's operational, so you're applying the lemma, you're not checking whether it is lossless strong or not. And you don't have to check because we prove the lemma is correct. So far so good? You just keep doing this. Very simple algorithm. There is a catch though. At the end of the day, if you keep doing this, is this dependency preserving? Well, we know this is not, right? Because you don't have to go further. Just look at this example. You can argue that this is the effect of using that lemma, right? I find this dependency that's part of the BCNF, so I use the lemma and decompose that into that. So this is you, right? And you stop, right? At this point, they are already in BCNF, I stop. I do not have to decompose any further. However, what do you notice? This is not dependency preserving, as we said. This is not dependency preserving. Dependency preserving. So what do? And this guarantee to terminate because the termination is easy to say because at the end of the day, you are left with two attributes. You cannot decompose that further. Right? So at some point, this algorithm must terminate. However, this may not give you a dependency preserving decomposition all the time. I will claim the following result before I show you an example. Then we're done with function dependency and normalization. Okay. Unfortunately, that's part of the reason why people define third normal form. By the way, I will skip third normal form altogether. And if you're interested, you can review that yourself, but I'm not going to cover third normal form in this class. Okay? So you can review yourself. Now, that being said, the reason why people need to define third normal form, if you may allow me to go all the way back. So the relationship is that if you are in BCNF, you are automatically in third normal form, but the other way is not true. In other words, third normal form is a relaxation of BCNF. In other words, if you understand the intuition behind BCNF, what that says is BCNF has no redundancy whatsoever. Your database is as minimal as it can be. There's no redundant data whatsoever. However, because of the observation we just made, which is it's not always possible to get a lossless join and dependency preserving decomposition into BCNF. So that's the fact. Like the ABC example I just gave you. You can get lossless join decomposition all the time, but it's not always possible to get lossless join and dependency preserving. If dependency preserving is important to your application, meaning you do not want to use assertion or trigger, you follow me? Then this decomposition might not work because you have to decompose into something that's not dependency preserving, has this echo effect. Right? Learn something new today. Cool. All right. If that's what you want to avoid using trigger and assertion altogether, so that you don't have to check constraint across multiple tables. That's the point, right? B, C, and F may not satisfy that requirement because the decomposition into lossless join and dependency preserving decomposition may not always exist. That's why people define third normal form, which is a relaxation of B, C, and F. In other words, it allows some level of redundancy to exist in the database. But this is not that trivial if you think about it, right? Once you do allow redundancy, an interesting challenge arises, which is what type of redundancies you should allow, and what's the degree of redundancy that you may allow. Of course, you want to. This is a really interesting challenge, which is you want to allow the minimum level of redundancy such that a lossless join and dependency decomposition, dependency preserving decomposition into that third normal form is always possible because that's the objective. You do not want to allow more redundancy than necessary, meaning you are already able to get lossless join and dependency preserving. You do not want to allow more redundancy than what's needed to enable that. Does that make sense? And how do you capture that? That's obviously not trivial, but people have studied this and they have defined third normal form, and they have shown that's the minimum level of redundancy that you can allow to enable lossless join and dependency preserving decomposition at the same time. Always, no matter what's your input and what's your instance. This is a really cool result, right? If you think about it. But it's a really deep result as well, so that's why I decided not to cover it. Okay? But if you're interested, you can read it yourself. So far so good? Okay, now that being said, let me move on with this example, and we're done. Okay, so let's look at this particular example. This is the example we mentioned before, right? This is the project example, right? If I move all the way back to the function dependency, this contract database example, right? Contract ID, project ID, part ID, quantity value, department ID, right? Who ordered what, under what contract, for how much, and how many. Right? So that's that database. Okay, so I'm reusing that database, that schema. Now I tell you C is the key, and I have the following function dependencies. Is this in BC and F? Is this in BC and F? First of all, is this in BC and F? Well, let's go through the function dependencies one by one. Key is the attribute C is a key, right? So C determines everything else. That does not violate BC and F because the left-hand side is the key. A key is a super key, so it's fine. So you satisfy BC and F. What about the second dependency? JP determines C. Does that violate BC and F requirement? Can someone tell me yes or no? Does that violate BC and F requirement? Go ahead.
Key can determine everything, but
say again?
Key can determine everything in the schema, correct?
Yes.
And vice versa should be all right as well, I believe.
You believe? Yeah. The reason is, if I add on to what you said, is because JP determines C, and C is a key, so JP must be at least a super key. I don't know whether it's key or not, but I don't care because BC and F only requires the left-hand side to be a super key. So by this point, I realize JP must be a super key. So this does not violate BC and F requirement. The left-hand side, as soon as you realize left-hand side is super key, it satisfies BC and F requirement. So second dependency is okay, check. What about SD determine P? Now this causing you problem. This is causing you problem because SD determines P, but P doesn't determine anything else. So SD only determines P and SD. So SD, in other words, the attribute closure of SD is just SDP, which means SD is not a super key, which means this has violated BCNF requirement. Follow me? All of you follow me? Now, if you follow this simple algorithm, it says whenever you find such a dependency that has violated BCNF requirement, decompose the schema with regard to that functional dependency. And we have found such one. So what should I do? I should decompose the original schema into R minus P and SDP. That's it. Right? Using this simple algorithm, right? This is the lemma, operational lemma we talked about many times. Yeah, go ahead.
So SD isn't a super key because it's not unique. Is that what you're saying?
No, it's not SD, it's not unique. Is that, as I said here, it's because of this. The attribute closure of SD is just SDP. It doesn't determine anything additional to those three attributes. So it doesn't determine anything else. Henceforth, it cannot be a super key because for super key, you need to determine everything else. Okay? Do I answer your question or not?
Yeah.
Okay. All right. So given this, I decompose this into R minus P and SDP, which is those two schema I show on the top. You follow me? SDP and CSJDQB. By removing P from the original schema. This is just applying this procedure, right? W. Then you decompose this into R minus Z and W. I'm just applying this lemma. And we prove that this lemma is lossless. In fact, you can check. The intersection of them is what? Is SD. And SD determines SDP, so the intersection determines one of them, so this must be lossless. Okay? Are you done? Well, you're not done. You need to continue, right? SDP is okay now. Because the only dependency here is SD determine P. With respect to this is okay because now SD is a key of this schema, so this now is in BCNF. What about this guy? It is not, right? Because you still have J determining S. Do you follow me? You have J determining S with respect to the second schema, but J is not a super key of that schema, obviously. The attribute closure of J is just JS. With respect to this, the attribute closure of J is just JS. So J is not a super key. So this, again, has violated BCNF. What do you do? Or you decompose that into JS and everything minus S, which is CJDQB. Just keep applying this second step. Right? So you end up with this. So we end up with these three schemas. Then we're done. At this point, we're done. Why is that? SDP is in BCNF. Because the only function dependency with respect to that is SD determine P, which is okay, as I argued. JS is in BCNF because the only dependency there is J determine S, which is fine. What about the last one? The only dependency there is what? Is C determine everything else. Remember, attribute C is the original key, right? So C determine everything else, so C still determine those other guys. That's the only dependency there, so it's fine. You follow me? So it is a lot. It is a dependency preserving dependency. It is dependency preserving. Yes or no? Is this dependency preserved? Many of you are shaking your head. Why is that? Go ahead.
JP determines C is broken up into.
Okay, very good. JP determines C is lost in this process, right? So J and P are now in separate tables. However, you have to be a little bit careful, right? Because using that example as I've shown you earlier, the RW example, right? The fact that two attributes are in two separate tables does not necessarily mean the dependency is lost. For example, in this decomposition, S and W are in two separate tables, but S determined W is not lost. However, in this particular case, you can show that JP determines C is lost. Why is that? Because if you write down the AND, the three schema in the AND, what is the dependency here? What's the dependency here? What's the dependency here? C determines. If you union them, you check the code of that, they cannot infer JP dependency. Nowhere you can infer JP dependency. So that's lost in this process. So this is not dependency preserving. But that's okay because B, C, and F, loss withdrawal and dependency preserving decomposing into B, C, and F is not always possible. It's not always possible. You may argue okay? So you may argue, the other thing I'd like to mention is that there could be more than one dependency in the original schema that has violated BCNF requirement. The order you deal with them will lead to quite different decompositions. In this case, we deal with SD determine P first. That's why we got SDP and CSJDQV in the first step. But you can also deal with J determine S first, which give you JS and what? And CJBTQB. And if you further go from there, you will end up with a different decomposition, but that's okay. The point is, there could be more than one possible decompositions. Loss resulting will not give you BCNF, right? And we actually saw an example of that. This is the one decomposition that's loss withdrawn and BCNF. I just show you the other one, right? Which is AB and AC. That'll give you yet another loss withdrawn decomposition, and the resulting schemas are BCNF. Right? So there could be more than one possible decompositions. That's okay. Final slides. Really just the last slide. Is that in general there may not be a dependency preserving decomposition to BCNF. Right? So for example, CSD, you have CS dependency, D dependency. In this case, the first dependency is fine because CS is the key. CS determines C and CS determines CS itself. So CS determines everything. So CS is the key. So the first one is okay. Second one, Z determines C, is not okay because Z is not a super key. So you decompose that into ZC and CZ. In order to fix that, you decompose this into ZC and DS. Right? But doing that, you actually lost the first dependency, CS determines D. Because C and S are now in two separate tables, and there's no way you can get that dependency back. Similarly, in our last example, as this JP determines C is lost. So you may argue, what if an easy fix to this is to just add an additional schema to enforce that dependency that's lost, which is in this case, if JP determines C is lost, in addition to those three schemas, let me add another schema, which is simply JPC. Let me just add that. In addition to those three schemas I have. It's an ad hoc fix. Yes, you can do that, but this introduces redundancy. Basically, you're storing this schema only for the purpose of enforcing one particular function dependency, which is really ugly. Right? So people don't want to do this. That's why they introduce third normal form, which is the relaxation of BCNF. And good news is dependency preserving and lossless round decomposition into third normal form is always possible. But of course, it's a trade-off. Trade-off is now you have to allow some level of redundancy to exist in your database. As I said, I will choose to ignore, drop all the content with respect to third normal form, but nevertheless, I have included all this discussion in the slide. You can review yourself if you're interested, but I don't require you to understand this, okay? Coming back on Monday's lecture, I will start something new called transaction, which is how to support concurrent access to database. I will be releasing homework 4 either later today or tomorrow, okay? Yes? People, please be quiet. You have a question? Go ahead. Yeah.
Third normal form will not be on the test, right?
Third normal form is not on the test, but anything we have discussed so far will be. Yes. Yes, go ahead.